Students need more students. Want to do something. To do something about overcurrent protection.
Okay, let's do. What is overcurrent protection and what we can do about that? Most popular, mostly used kind of protection is overcurrent protection. General idea of such protection, overcurrent or maximal current protection. We have some protected object, let's say line. We use current of the object as an, let's say, our operation signal. We have device with nostrad. Nostrad means tree. Or simple, current is bigger than a tree current, and if so, this connection signal, I can draw a nice fold here. So if current is over the limit, we should discontinue energy supply. Looks nice. Here, for example, where am I? Here. Old circuit breaker. What we got here? Coil, inside is a core, and a spring. If current is over the limit, it triggers mechanics, current flow to the coil, on disconnected. Simple, instant overcurrent protection. Okay. Let's try to look deeper. And what to look deeper? I will assume very simple network. It will be, let's say, distribution network 10, 11, 24 kilovolts, something like this. Source, one switch, one line, and one load. Let's say it's a 10 kV network. It's a distribution network with the isolated neutral network. Point number one. What's here? Oh, it will be, of course, transformer and 0.4 kilovolt connection, something like this. One thing we need to understand about the load. It's called inrush. What's in here? It may be air conditioning, for example. What will happen? Let's say power was disconnected. I don't know why, and we turn the switch on. What happens with the air conditioners? Yeah, they start. Magnitude of current, time, start up of a synchronous machine. Water pumps, sewage pumps, all will do something like this, but that's not all. In modern days, many loads, like digital equipment, modern lighting, all kind of frequency converter and so on, they do have or single phase bridge on the input or three phase bridge on the input. They all will have a DC link or DC stage at the input. At the moment we switch power on, at the moment we connect back network to the power, this capacitor charges. This capacitor charges. And we will see what? Surge of current. Again, we will see inrush process like this. Current will now fall to the zero. So, first moment we need to care about. Before any fault, before anything, we should remember inrush current of our load. This is normal current, and this peak inrush current what appears when load is energized. They are characterized by a factor. Inrush factor or startup factor. In Latvian, startup is a Powation, so I will use Powation's coefficient in Latvian. It's an inrush factor or startup factor of the load. Our protection should have a trip current or in Austrian, it is from Latvian trip, it's a trip current of my protection. It should be higher or equal to 1.1 multiplied by startup factor and multiplied by E, or it will be, if in Latvian Sourcen, it's a load current maximum. Why this 1.1? Because error of my current sensors and my relay too is 10%. I rely on equipment 10p. If someone pays me better and I have a 5p equipment, so it will be 5%. Okay. You can already see that something is bit sensitive. But let's go bit deeper. So first I need to note 1.1 multiplied by startup factor and multiplied by max load current. Максимал load strain. it's 0.1, but that's not all. I will go a bit further. Word not important. A, P. Very simple network with load on substation. For example, we have a fault on a distance from the beginning of the line. I can draw a chart. It's a distance till fault, current, this current through the protection. One line, it's an Ohm's law. This one will be A, B, C, three-phase fault, and this one will be line to line. It's approximately square root of 3 divided by 2 between these lines. Approximately. So current of fault as a function of distance. I can also draw line like this. It's a max possible load current. Max possible load current. Yeah. What I got here? Oh. I got here a problem. What kind of? Let's look here. I need protection A. This will be my protection device based on max current function. It should be sensitive. What's the protection area? It will have current and it should produce a trip signal for this switch. This should be sensitive. What a protective area for this device? My device RA should protect all this area. So it should be able to disconnect any fault in area A. This means I need one digit. It's a minimum possible current of internal fault. Look at this point. I will mark it with the 1. 1 minimal якше. Point 1 is a minimal possible internal fault current. Minimum possible internal fault current. My device should be sensitive. This means what? Approximately 10%. Trip current of my device should this is my line. it's a trip current of my device. No, wait and trip. Trip current of my device. So this line is 0,9 of E minimum internal. 0,9 of minimal possible internal current. My network is isolated network. That's why I consider only one-to-one faults. Okay, and what do we see? Where is the actual end of the protective zone? Here. Here is the real end of my protection zone. My device is sensitive but not selective. It will treat falsely on external fault. For example, this fault, current is here. Here is the current of this fault. My device will trip, my protection device will trip falsely and disconnect this current instrument. This fault I draw is in the protective area of device B. Device B should disconnect it. If device A disconnected, I was customer. Non-selective operation. My bonus will fly away. This is not good. This is definitely not good. This is definitely not good. What should I do? Maybe I should try to make it selective. Where is reference point for So, where is the reference point for selectivity? The reference point for selectivity is called maximum external fault current. For sensitivity, my protective device should be sensitive for current, minimal internal current. If it operates at minimal internal, it will operate on any internal fault. To be selective, it should not operate on maximum external. If it's not immune to maximum external, it will not operate false on any external fault. Where is the maximum external? Where it is? Something like this. The point 2 is a maximum external current. And I will need to take 10% and draw, for example, yellow line. This line is 1.1 T max external. Why 1.1? Because I predict error of 10%. What can we say? Nothing good. Here is our real. This is our real protected area. We protect only small part of the line, approximately 1/3. we see problem. I can appears that I cannot create an operational protection because it's either not sensitive or not selective. Yeah, that happens because I'm trying to fulfill two criteria with one parameter. I need a second coordinate. Two criteria that have two coordinates. So I will change logic of my protection. I will make it more complex. It was good drawing, but simple logic current trip signal to discontinue do not work. I will switch to different logic. Here is my different logic. I will take current of phase A, current of phase B, and current of phase C, each to the element current bigger. If any of them three, I will activate delay function. What is it? 9762, sorry. Oh, here it is. Delay function. Coil and a clock. If I put a 1, digital 1 to the input, what happens? Count, oops. Trip signal generated. And what if signal disappears premature? It returns to its initial state. Up, trip generated. Here is a set of contacts. If disappear premature, returns to the previous state. All time thing. Of course, now it will be simple piece of programming code, but it illustrates well. So signal to disconnect switch will appear only if current on at least one phase is bigger than a trip current and it persists during time set of delay function. We can return to our network. Here we'll see protection device A, protection device B, second line. This will be D, for example, with load, and E, not important. My simple distribution network, for example, 10 kilovolts. It's an isolated, natural, simple network. Same chart. Distance, current through the device. phase. I start to write in Latvian. And what's here? Here should be the yellow line is a load. It's a maximum load current. I need to select trip current. Where's the bottom line? Load current. Yeah? If I disconnect my protection from the load current, possible I will need to seek for another job. So for P, I can draw something like this, maybe in different color. This will be trip current for the P protection. It's 1.1, 10% safety gap. And the same thing this will be trip current for the A. Nostrada in Latvian means trip. Or maybe. Will my protection operate sensibly? What's the effective protected area? Oh yeah, effective for A, effective protected area is whole network. You see? Whether here is minimal fault. Here is my trip current. So I'm very sensitive. But what about selectivity? If the trip time would be 0, what will happen? This fault, this red fault. Here is the current of my red fault. What happens? For both protection, trip current is below the fault current, so both will start. Now, hey, I need to care about selectivity. And not what we do. Here is the trip time for my devices. I will set, because I need to care about D, I will explain. I will set 1/2 of the second for the B, and okay, it's in a strain. No, it's not. Should be close. 1 second for the A. This line is delay time or trip time for the A. What will happen for this fault? For both protections contains sections of current bigger, and this section is linked to time delay function. What will happen? I have here 3 phase, so all 3 time current bigger sections will work. And here will be logical 1, yeah? This logical 1 will start time counting. What happens next? What happens next? Here is the clock for device B. Hop. It should, okay, I should say to half second. Okay, it's 3.5 seconds. After 1/2 of the second, disconnect signal is sent to switch B, and what? Fault is cleared, current disappears, and what happens with current sensors on A? Current disappear. Current disappear because B switch cleared the fault. Current disappear. At this point, 1 changes to 0. Yeah? Yeah, because current disappeared, it's no longer above the orange line. Current disappeared. 1 at this point disappear, and the clock of A returns to its initial state. Yeah? Switch remained closed, nothing happened. Selective operation. Yeah, I've got relative kind of selectivity. My two protections to protect the device are separated in time. In structure like this, what I got? In case second line is fault, B protection device trips first, clears fault, and A returns. In case fault is on the A line, this will count to 1 second and clear the fault. Sensitive, yeah, I'm covering all possible internal fault. Selective, yes, selective, and more of that. What will happen if, for example, I have this fault, but this something happened here, and fault wasn't cleared in half second? What will happen? Time function at protective device A will count 300 milliseconds. Current falls, fault don't clear. 500 milliseconds. Current falls, fault not clear. 6, 7, 8, fault not clear. 1 second, fault not clear, send disconnection signal. So it will clear fault as a backup protection. If main protection fails, in this scheme, backup protection waits half second more and clears the fault. This system not only sensitive, selective, it's also more robust because next upper protection on the supply chain acts as a backup protection. And what's good? It's completely independent. When you have backup protection on the same substation, in case of substation fault, for example, own power supply of substation fails, near backup also fails. Here I have so-called remote backup or far backup. In case of far backup device is absolutely independent from the main. Here I have absolutely independent backup scheme. Very nice. This thing operates and operates well. But I need to point some moments. Moment number 1. What about this half second, 1 second where I took these digits. Why half seconds? Why 0.3 or maybe 1? This gap between between protection operation time 1 delta t. This time spread I cannot select it absolutely freely. On the one side, at the shorter, the less negative impact from the fall should be expected. So it's preferable to have it as small as possible, but I cannot reduce it infinity. Moment number 1, this gap should be long enough to next switch for the next switch to interrupt current. Current should disappear, fault current should disappear, fault should be cleared within this gap. So it includes several components. On trip time of the protection, nothing in this world works absolutely instantly. So some time is needed for protective device to calculate, to understand, oh yeah, current is bigger. Second, on operation time of switch mechanics, and the main component is arc extinguisher time. It depends on the circuit breaker design. Very old oil circuit breakers needed up to 1 second to clear current. Old oil circuit breakers, more modern circuit breaker with small oil chambers required some good time was half a second was a very good time. For the SF6, you can safely use 300 milliseconds. Shorter time is for vacuum breakers. For vacuum breakers, disconnect current very fast. Actually, you can risk 200 milliseconds, but usually no one wishes to take a risk and use 350 milliseconds, something like this. In our case, we often put as some gap, you know for what? For frozen oil. Mechanics, during the winter freeze, mechanics can operate slowly because grease freezes. For hotter lands, 300 will be enough. So this time space, this time difference mostly is determined by ability of the circuit breaker to interrupt fault current. Point number 1. Actually, it's answer to the question, how old is your network? How old is your equipment? The older equipment, the longer it clears fault. That means what this time spread should be longer. It's one. Second thing, you need to understand one moment. The yellow line. The yellow line max possible load current. Inrush of your load. with something like this. It's what happened. I don't know. It was a fault. We cleared a fault. Approximately 60-70% of all faults are not persistent. Lightning strike, some kind of branch, many of all you call, where is this? People driving construction equipment under the line. Very often. A lot of faults when people carry excavators and something like this, large construction equipment, and they touch the wires. They will go, this fault will disappear. All kind of tree branches. Most faults are not persistent. They do not remain. Remaining faults, something like poor fell. And it's highly expectable that when you reconnect line, everything will go back. But what will happen? Before, voltage was 0. You connect the line, everything connects, but you see in rush of your load. In case in rush, this point, maybe 3, 5, even 7 times higher than the nominal, compared to stable regime. If there would be no delay, this is our load current we need to think about. But we have delayed action. Our protection will not trip instantly. This means what we need to take our, and this point is our reference point of load current. And it's only, usually, very common number, it's 1.1, 1.2 of the nominal. So, 1.2 startup factor is typical, not 5 or 7. It has a huge difference. Your protection will be more sensitive because it's operate with delay. Fine. What's not fine? One second. Socks. 1, 2, 3, 4. A, B, C, D, E. And of course, lots. Distribution networks are meshed. How we look time chart. Trip times or add selections. Add select. Disconnection time. For the F, only 1 delta T. For the B, it will be 2 delta. Nice. For the C, we will get +1, 3. For B, 4, delta time, yeah? And for A, it will be terrible 5 delta t. Or 2.5 seconds. This 2.5 seconds. It's not good. For small network, one operational stage is okay. But for larger network, for network with a lot of lines, we'll see, but it's not, it grows out of control, out of acceptable time delay. And what's worse, the most, here is our source, and it will be transformer substation from 110 kilovolt network. The higher current will be here. The higher current, longer clearance time. This means what? High damage. Approx damage from the fault is current square multiplied by clearance time, amount of heat. I don't like it. What can I do? What can I do? First idea. A, B, C low. Fault current load current. It will be some load. It's a three-phase A, B, C fault. Distance, current through relay, fault current. What can I do? First, I will set, this is C, this is B with 1 delta time, and let's say this is A. That's how it looks without any, in the previous version, flat 1 over current. I will change my design once more. I will have A phase current, B phase current, C phase current. This one is simple delayed operation. That's a white one. I will add one more. I can use, because it's an isolated neural network, I can have 2 relays. Can have 3. At last, I need A and C. I will add an instant stage to my design. Instant stage with 3 1 E max external. Where is my maximum external current for the A? This one. E max external for A. This small fold. So I will set trip 1.1 multiplied by E max external. This is trip condition for this instant section, or instant, it's often called a stage. This will be first stage, instant stage. It will trip instantly, but protect only this part of line. So I will have instant stage, maybe I'll draw a time chart. Time. So for this, I will have instant stage A1. It is fast, but do not protect the whole line. It protects only, is 2/3. In real life, sometimes you'll be happy to get protection for 10% of the line. And I will have delayed stage. Delayed stage protects all line. But with the time 1.5 seconds. This will be A2, delayed stage. Same trick for the B will yield me B1, small instant stage, and B2 delay. Okay, C will operate, let's say it's only one stage. Here is a chart tripping time chart for the two-stage design. It's an old school protective device here. Old school protective device. Set 2 overcurrent relays for first stage, these two. 3 max current relays for the second stage. Time delay function for the second stage, this one, this clockwork. Also, it has, this relay is a disconnection pulse relay. Idea, what current, fault current, we have no guarantee what fault will be absolutely clear, so fault current may be disrupted with some, not something stable. To make protection more reliable, several things are added. Special function, I will draw it like this. It's a TOF type of time. It's a special delay. Do I have one? Oh, this one is good. All state. this relay. It has a copper cylinder in its system. It has a coil and this copper cylinder. When the coil is energized, it strips and connects its contacts. But if you disconnect the coil, current will continue to flow in this copper cylinder, self-induced current. And relay will remain in on position for some second. It ensures what? Disconnection pulse is stable and reliable. So this section is added to keep the switch off pulse, because current may, during the fault, something burns, current may appear and disappear and appear again. So if we have free condition, disconnect signal should be taken. This one is small one. In a time where the leaf is bigger. For real hardcore system, this is this relay of disconnection pulse. Real high capacity thing. It's not very old. This one, when it's produced, it has number 80. It's younger than me. This is real. This copper cylinder will maintain its close for second or second and a half, something like this. And what are kahash? Who are kahash? Ka means relays. What means ash? It's a special signal relay. Do I have one? It should be somewhere here. Kahash, where are you? Who took my signal relay? Here it is. Old style. Relay. It has a coil. Oh, come on, trip. Okay. Yeah. Hey. Yeah, I got it. Here, what happens when it trips? It's a special relay. Hey, come on. They should trip if you shake them. No, not willing to take it anymore. Hey, you. Oh, yeah, I got it. Now it's tripped. It shows kind of radiation sign. This is older version. I don't know
What happens? Where are cities?
They're somewhere around. More advanced version showed red, kind of red banner, but it's not important. It's a relay to do what? It's a signal relay. This one, overcurrent stage trip, max current stage trip, protection trip. To understand why line was disconnected, it's good to know what happens. So, see, section 3, relays on the bottom. They are to indicate what happened. Signal relays. Of course, for modern protection, it's set of 3 overcurrent and 4 overcurrent relays. They have digital memory and nice LEDs showing all my protection tree. Yeah. A, B, all have some load. They also load, not important. So how can we, what kind of system we will have? C1, B1, B2, A1. In modern days, we can have this thing, A2 and A3. Modern relays allow up to 5 zones. This old-time monster allowed only 2 zones. Modern relays is very typical, but you can have up to 5 protection zones. So this is called one zone. For the last one, here, they are spaced by 1 delta T, here also space 1 delta T. One or 2. What will be trip current for B2? Will be here current transformer connection factor. SCHE means schema. It's coefficient of schematic. For, I can predict it will be 1. It's not 1 only for current difference. If you find a current difference scheme, look at my previous lecture. Go to your boss, can we please change it? Maybe it will be in the next plan. Factor of schematic. What's next? From Latvian Polish, it's a startup factor of your load. It depends on your load. Take typical 1.2. Special cases, your load is one huge asynchronous motor without self-starting. Special case is something like huge water or oil pump. Take a bit time and calculate real startup factor. It may be high, it may be up to 5. kind of monologue, the most typical with high, real high startup factor, you know what? Python kind of air compressors. They have a very high startup factors. Also, large fans with large inertia. And large water pumps, irrigation pumps, megawatt scale, real large. In this case, this factor will be much higher. It's possible, it can produce a problem. Next one. It's a D from Latvian drošum. It's a safety margin. If you have 10p sensors, it will be 1.1. For 5p, 105. It's a safety margin for the error. For usual equipment, it's 1.1. From drošum, it's a safety in Latvian. So it's a safety factor. Divided by two factors. Transformer scaling factor. Here, take a note. For older relays, you need to program current in amps, in secondary amps. For modern relay, you program primary amps, but you program, this is ratio of your transformers, of your current sensors. For modern digital relays, if you have analog sensors, you program their ratio as a separate setting. This will be as a setting in relay. For high-end digital substation, you don't need to program these two relays. This is programmed to transformer interface. But this is, it depends on how your, it's a factor, ratio between primary current and secondary. It depends, should it appear in this formula or it's simply a setting for relay, it depends on the way your relay is programmed. Older relay require this to be in secondary amps. Modern relay accept this in primary amps, so you do not use it in formula, but you set this factor inside relay parameters. Also, return or hysteresis factor of your relay. For old relays between 0.8 and 0.9, for example, for this old monster, this type of relays is the commission margin 0.83. For modern digital relays, very typical is 0.96. 4%, maybe 5%, 0.95. So for modern relay, it will be something like 0.96. Actually, it's programmable. Inside, deeply inside relay setting, you can select this factor, but do not set 1. You will have multiple trips because current is not so stable. You need to set some return margin. And here will be slot maximum load current. This formula is for last stage. So for B2, it will be, here will be second load. The same formula will work for A3, but here we will need to set L1 plus L2 all loads. This formula is for the last stage of overcurrent protection, or max current protection. It depends on load current. Okay. Next one. Instant stage of the beat. What's the criteria? Here, not should draw here, but not important. It should be scheme, no startup. It's not interesting because it operates from the fault current. Safety divided. If this, again, if needed, ratio of current transformer for modern relay, it's a separate constant inside relay parameters. For all, this old type, make this type operation amplifier based and so on needed current SS in amps. Digital relays, modern, usually are programmed in primary values, and this is hidden inside relay parameters. You always need to set ratio. Return factor E max, maximal area boeing. In later it will be maximal area boeing or maximum external fault. Here, three-phase fault. This is maximum highest current of all external faults. Scheme 1, safety 1.1. You get it. A2 stage with this point should be coordinated. It's a very important word here. We need to coordinate protection. We need to ensure selective operation. I have two coordinates here. I will draw it. Time coordinate. And what about this? It's a current coordinate. I need to ensure 10% margin between these lines. Meaning what? Trip current for A2 should be scheme should be 10% from the I don't need I with 1. What's an I with 1? It's a maximum external fault current for the next stage. For the A2, I take, because I need to ensure 10% gap here. This means this point, where delayed stage changes into instant, is determined by max external current of this line. this stage second of the next line, or the previous, actually the previous, coordinates to this point, and it takes safety factor square to ensure this gap. It's important. Middle stages are coordinated to the next line external formed. Not on, but next. And A1 will be coordinated. This is number 2. Trip current of the A1 will be scheme calculation, questionable, not always needed KTA, 2, so E marks external of the stage A. You don't see return ratio here because it's not needed. Instant stage, this stage is instant. Return when the current is always 0. So return factor E do not need it. Nice chart. There is also another way to represent the same thing. Selectivity charts. Selectivity charts are drawn in coordinates current, time, and always in logarithmic scale. They are always logarithmic. Here I need to draw what? First, line E load 1, E load 1 plus E load 2. Next, I2 and red I1. Now I can create long zone of B2 operates in half seconds, yeah? Or, no, in 1 second. C1 operates in short time. This is C1. Maybe, okay, like this. It should be 10%. It's C1. Next, B2 and 1.1 and with time 1. Here 1 second, and this one is 1.1 I1. So this one is B1. Operational line of protection B. For protection A, I will have what? Have 1 second. I will have something like this. 1, 2, here. Wait 1 second. I better draw one. Yes, instant. Maybe one fails instantly. For A1, it has instant operation here. So from this point, it operates instantly. It's an A1. This is A3. Here A2 and this is A1. Oh, approximately something like this will appear. It's an selectivity chart for my set of 3 small protections. Current can go higher. Yeah, something like this. Like this. It's C1. Actually, it should drop deeper. Why? It's one flat, so I can go like this. It's not problem. It should go deeper. Nice chart. Here we can see who's cooking who. Actually, we see every mergence. Maybe here should be 10%. Big. Like this. Always should be at last 10% margin. If I have a 10% safety. If I have a 10% error, current measurement error. Okay, what's next? One tiny problem. And its problem is over voltage protection. Lighting protection. Over voltage protection, these charges. In old style, they were like gaps like this, one side earth and one to the line. If lighting strikes into line, there arc appears here and runs up. That's the way over voltage is discharged. It's of course an obsolete technique, modern used nonlinear resistance. And they are able to interrupt current. over voltage discharge trips, for short time high current arrives. In theory, with digital relay you can set a trip time to 0. So the instant zone will trip instantly. It's not a good idea, you need to set some time. You need to give some time space for over voltage discharges. This means what minimal trip time should not be 0. Set some 60, 70, 100 milliseconds. With old relays, electromechanical, it was set automatically. With digital relays, do not play to the limit, do not set a 0 time. There will be a tiny delay due to Fourier filter, but do not risk set at last 50 milliseconds. So this should not be 0, but should be at last 50 milliseconds, better 100. It's not changed much, but it should be. Because of over voltage discharge. This is one. Problem number 2. What's the problem number 2? Sensitivity. I've said the way I draw, it's like one load at the end substation. In reality, with distribution network, you will have many these ties, client connection, client transformer along all your line. This is all your load current. It is good management, good practice to design your protection sensitive enough to trip. So each disconnection is transformer and the bus to trip on the client side fault, even if it is not yours. In different situations, mine, not mine, maybe on transformer, inside transformer, it's stupid. Sometimes it's here, sometimes it's here on the transformer, sometimes it's here, this border. Take into consideration fault here. Even if they are very different, take the, of course, the bigger one, but the deeper you can go with your third, or not third, last stage, what we call it, last stage, it's better. And the next moment, very important, when your project will go to expertise, into commission, you need to prove your protection scheme is operational. There is one thing you need to prove, sensitivity of your protection. I have schematic A1, A2, A3, and B1, B2. You need to prove your protection is sensitive enough to operate on the smallest or minimal internal fault. Here, line to line fault will be what? 3. Fault free. You need to calculate so-called sensitivity. In Latvian, jutikums is sensitivity. Sensitivity factor. It's roughly it's an E minimal ear shape, which means it's minimal internal ratio of minimal internal current to the trip current. This, for all relays, you should compare relay currents. For modern, you can use primary, so only comparable. For all time relays, schematic factor should be taken into account. Here, you can compare, modern day you can compare in primary arms, but anyway, it should be more or equal to 1.2. It's very good connection, maybe 115, but it's really it should be 1.2. This means that current of minimal internal fault should be at last 20% over the trip current of the second zone. For the long line, no problem. If you design for the cities where lines are short, this may not happen. This means what this A2 nice zone may become irrelevant. And your actual protection will become this. So this A2 will not work, for in my example. May appear at this, if the third zone is sensitive, okay, you will go through. There may be a question on system stability, or in a very important substation. If you have a limit, a strong limit on the fault clearance time because of system dynamic stability, you're in problem. This means that you will need different type of protection. Overcurrent will not work here, or max current will not work. For ordinary network, if next zone works, okay, you will get your width question. But if next not work, you're in deep problem. You need to you need much more expensive protection scheme. This check is mandatory. You cannot omit it. So you need to prove that your protection is sensitive enough on internal fault. So a trip here for current scheme, trip current should be at last 20% above minimal internal fault current. And it is possible that you will not be able to fulfill this, meaning what you need different, more expensive protection. Okay, I understand my time is ending. Maybe some questions? Online, maybe someone?
I'd like to ask a question. Silence.